Alright, hi everyone. Welcome to the second video on the chapter of hydrocarbons for chemistry. Right, so I think as mentioned in the first video itself, I mentioned that we have learned about the concept of homologous series as well as the specific group called the alkenes. Now in this video, we're going to learn about the second group called the alkene. Right, but before that, just a quick recap. Right, in the previous video, you have been introduced to this set of homologous series called the alkanes, and these are also what we term as saturated hydrocarbons. Right, so just a bit of a recap. Right, saturated means that they are hydrocarbons that only contain single carbon-carbon covalent bonds. Right, and we also mentioned in the previous video that we do need to know that each carbon atom is capable of forming up to 4 bonds. And why is that the case? Is when we look at the atomic structure of carbon itself, we'll know that it has an electronic configuration of 2,4. Right? This will mean that given that carbon has such an electronic configuration, it will only be able to form, or rather, it must form 4 bonds. Right? So in the case of alkanes, you see as that 4 single bonds, that single line that you see over there, indicated here in the blue lines. Right? So each of the carbon is as such. But when it comes to alkene, you realize that it has a different what we call functional group, right? But the logic of having 4 bonds will still apply. So what do I mean by that? Let's take a look. In this video itself, we are going to learn about alkenes, right? These are what we call unsaturated hydrocarbons. In addition, there's a certain general formula to them as well. We'll learn about their drawing, we'll learn about their physical properties as well as their chemical properties. We'll also be learning a bit more about how do we actually manufacture alkenes by this process called cracking. Also, we'll talk about a bit about the comparison between saturated and unsaturated hydrocarbons, basically in terms of alkane versus alkene, and we'll learn about this reaction called using bromination, right, to differentiate the two. And lastly, we'll end off with learning a bit more about these things called polymers, but that will be covered in greater details at the very, very last chapter of the year. So, first up, alkenes, right? Alkenes have a different general formula, right? Alkenes' general formula is shown here on the screen, CnH2n, whereby N refers to the number of carbons, and this time around you realize that the N starts from 2. It's not a typo over here. It needs to start from 2. And that's because alkene have a very special functional group, and that's called the carbon-carbon double covalent bond. C double bond C. You see a double line here? This is a representation of that double covalent bond. What do we mean by this? If you recall, in Sec 3 we learned about covalent bonding. Each line represents a single covalent bond, and that represents a pair of electrons. So if you look at the dot and cross drawing on the right hand side, you see that the single lines are represented by the pair of electrons. Within the 2 carbon, which is where the double line is, the double bond, that's where you have 2 pairs or 4 electrons over here. Right. So alkene actually are special because they have these carbon-carbon double covalent bonds, and because it must have these, each time you can only start with at least 2 carbon, hence N must have 2. In addition to that, if you look at the drawing carefully, zooming in on the one on the left hand side, you realize that each of the carbon has a total of 4 bonds, just like what we said earlier. But this time around, one of the bonds is a bit more special. It is a double bond, but still it is 4 lines, right? It's different from the case of alkanes, whereby it's 4 single lines. But over here, there is still 4 lines, just that one of it is a double line, a double bond, right? But the logic is still the same. So the idea of each carbon must have 4 bonds still holds. But whether these bonds are single or double, it differs for alkane and alkene. So, in terms of the members of the alkane family, right? In terms of the formula, right? If you use the general formula of CnH2n to derive the molecular formula of the alkene, you know that for the first one, which has 2 carbon, it will be C2H4. Now, if you recall in the previous video, we learned about the naming of organic compounds, right? When there's 1 carbon, we start with METH. When it's 2 carbon, we start with ETH. 3 is PROP, 4 is BUT, so on and so forth. That will be the prefix, the first word that comes along. The suffix, which is the next part of the word, depends on the series they are looking at. So in this case, if it's an alkene, it will be called ethene with 2 carbon. In terms of the drawing of the alkene, we will still draw the 2 carbon. This time round, there must be a double bond between the 2 carbon. and then that's where your H fills up the remaining possible bonds of the carbon. Try this out for yourself. You might want to pause the video to try and derive the formula, the name, the drawing for the one with N is 3 as well as the one with N is 4. Alright, and now I'll be revealing the answers. For the one with 3 carbons, there will be C3H6, name-wise propene. In terms of the structural formula, which is the way we draw out the bonds and the atoms arrangement, it will look like this. In terms of the the one with N4, there will be C4H8, it will be known as butene, and then this will be the structure. Now, as you look at these structures, what I want to highlight and to take note of is that each time we draw the structure, there is only one set of a double bond. Now, this is not always the case, but generally in your syllabus, when you're drawing the alkene structure, you are usually given those that only has one set of double bonds, right? So just for your info, for alkenes with 2 sets of CC double bond, we actually give them a special name. The name is called diene, right? But this is not required at this point within your syllabus, right? So most of the things that you are used to drawing now is just in a normal alkene, which has only one set of the CC double bond. Other than that, the remaining carbons are actually attached by single bonds, as you can see in the drawing. So likewise, if you do a proper count of the number of bonds around the carbon, you realize that it will still be 4 bonds, right, as mentioned previously. So if you take a look at butene, for instance, right, for the first carbon on the left-hand side, we have 1 bond, 2 bond, 3 bond, 4 bond. For the next carbon, it also has 1 bond, 2 bond, 3 bond, 4 bonds. Of course, some of the bonds are being shared. For the next carbon, there's 1 bond, 2 bond, 3 bond, 4 bond. For the last carbon, there's 1 bond, 2 bond, 3 bond, 4 bond. So it still holds about this carbon requiring 4 bonds to be what we call electronically stable, right? To have a completely filled valence electron shell. So this is about the naming and as well as the drawing as well as the formula. But don't forget, there's also this concept called isomers, right? So if you recall about isomers, which we can try this out here, isomers refers to different structural formula of the compound with the same chemical formula. So butene, since the alkene, N is 4. Since the formula is CnH2n, you know that it's C4H8. So a typical drawing of butene, we could just start off with just drawing the carbon, 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 just 4 normal carbon along the way. Of which then we start to put in the bonds. But remember there can only be one set of the double bond. Okay, so now with this thing, then we start to fill in the other hydrogen atoms, but knowing that each carbon must have 4 bonds. So you have your 3H over here, you have your 2H over here. The usual problem comes in when the student reaches the carbon that's involved in the carbon-carbon double bond. They might start to draw extra hydrogen. But do a proper count. There's already 1 bond here, there's 2 over here, so this carbon only needs 1 more. Now it doesn't matter whether you draw it on the top, on the side, or at the bottom, right? So I'll just draw it on the top in this manner. The last carbon, we notice that it already has 2 bonds here, therefore it needs 2 hydrogen, and this is where the 2 hydrogen goes up. Right? Similarly, it doesn't matter whether I draw it on the top and right side or top and bottom, so long as it's attached to the same carbon. Now, what could an isomer look like? This time round, a possible isomer of this butene could actually look like this, whereby the double bond actually changed in terms of its position. Because this time round, it shows that the way it's being arranged is different. If you end the hydrogen, you will realize that the 2 carbon in the middle now only has 1 hydrogen for each of them, whereas the 2 carbon at the end, we have 3 hydrogen for each of them. This is an isomer because it shows how the structure is actually different, because the double bond has shifted, the way the H is being connected is different, but the formula still stays the same. So that's one way to look at in terms of a isomer. Alternatively, it's also possible to say, what if the alkene is actually branched? Remember in the previous video we learned about the branching of alkene. So similar over here, you can also have a case whereby you have 3 carbons in the same row, but their carbon actually branches upwards, right? So how could this look like? Perhaps it will be single bond between these 2, and then a double bond between these 2. Similarly, now let's put on the H. So you have your H here, H here, H here, H, 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 and the one at the top can only have 2 H's because each carbon can only have 4 bonds, right? So when you look at all these drawings, you may realize that that means there is a different in terms of the way they are being arranged, and that is what we all know as a structural isomers, right? So in terms of the name, just for your info, additional info for you to take note of, how do we actually differentiate their naming? The first one that is shown over here is actually in chemistry we call it but1-in. The one on the second one we actually call this but2-in. The one on the extreme right side we actually call this let me think through about the name. Okay, this will be called 2-methyl propene, right? So I think naming wise is not an essential thing for you to know exactly how we actually go about naming it. This is just to introduce to you the different variations of the names when you are looking at isomers. Now some students might then also ask, for the second one in the middle, right? Can I then say that, let me shift the carbon-carbon double bond one more time to the extreme left side. So this time around, my drawing is as such. Would this then also be considered an isomer? Because technically it looks like I'm actually moving the hydrogen, moving a double bond towards the left side. But unfortunately, this is not an isomer. Why? Because these two are actually the same. It's just a way that you rotate the molecule, right? So I know this part is a bit hard to visualize. So when we go back to class, the teachers will be using some models to help you understand how do you look at these two drawings in particular. But for the case of butene, there are actually only these 3 possible isomers. It's just to highlight again, the last one that I drew, that I crossed out the red one, is actually not considered another isomer because it's the same thing as the very first one on the left. So let's move on to talk a bit about how do you actually form alkanes and alkenes. Now, alkanes and alkenes are formed by this process called cracking. Right, cracking is exactly what you think the term means in terms of the in the dictionary. It just means to break down stuff into smaller ones, right? But this time around, what do you break down? You break down long chain hydrocarbons, that means large molecules, into smaller molecules, small alkenes and small alkene, right? For this process to happen, you need a catalyst, right? As you know how catalysts work is that they will actually speed up the rate of reaction, right? How do they do that? They speed up rate of reaction by reducing the activation energy required for the reaction, and this will affect the frequency of effective collision, so on and so forth. Why is cracking important for us? Cracking is important because we want the smaller molecules as they can be used as fuels, and we also want the smaller molecules which can then be used to use as starting materials to build bigger materials. Last but not least, this is also used to produce hydrogen gas. Now, why is hydrogen gas important? This is actually needed for the one that we have learned earlier this year, Haber process, to form ammonia. Right? So to form ammonia, we need H2. So where does the H2 come from? It actually comes from a cracking process like this. So how do we actually go about deriving what is formed in the cracking process, right? It's actually not very complicated. Right? All you need to do is to count the number of carbons on the left hand side as well as the number of hydrogen and compare to the right hand side. Because cracking is just saying that you split them apart. So the number of atoms must still stay the same. So if you look at the first equation that I have over here, you have a C18H38. In the process of cracking, it forms a blank plus C2H4. 6 of them. Now, 6 of them of C2H4 will mean that there's a total of 12 of the C. There's also a total of 24 of the H that's being formed already. So what are you left with? You'll be left with C6H14, which is the remaining of the carbon and hydrogen if you just subtract the numbers. So that's actually how you derive a cracking equation. Very, very straightforward. Right? So you'll be given an equation, there'll be a blank, and you derive what is the product that's being formed. Right? The second one, C18H38. This time around, you form a CaH16 plus a C10H12. So in total, you already have 18 of the C and you have 36 of the H. Right? So then if you look at the original formula, that means you're only left with hydrogen H2, and that's it. Right? So that is what cracking is about. Right? Know about the importance and know about how to construct the equation. Let's take a look at the physical properties of alkenes then. You'll notice that the next few slides of physical properties of alkenes actually resembles the physical properties of alkenes. In fact, there's a few typos that I need to change later on. And the reason is because they are actually in the same description. So similarly to for alkenes, the melting point and boiling point actually increases when the number of carbon atoms increases. Because the larger the size of the molecules, the stronger the intermolecular force of attraction. Right, so you see some data over here. On the next page, there's a typo here. So alkenes, density increases similarly because molecular sizes increases. Alkenes also do not dissolve in water, but they dissolve in organic solvents such as benzene and alcohols. Alkenes, the larger they are, the more viscous. Right? Viscosity, if you recall, it means how difficult it is for it to flow. Right? So the more viscous, the harder it is for the chemical to flow. Okay. Another typo over here. In terms of flammability, similarly, the flammability of the alkene actually gets lower when it gets bigger, right? And the reason is because as the percentage of carbon atoms increases, it becomes harder and harder for complete combustion to happen. Typo here as well, right? So chances are the flame will be a lot smokier, okay? But what differs this from alkenes is actually the chemical properties. Because for alkenes, if you recall, I mentioned that they are actually not very reactive because the carbon-carbon single bond are not prone to reactions. But for alkene over here, right, you'll notice that they are very reactive because of the carbon-carbon double bond. And they go through two main reactions. First one, not new to you, burning or combustion, right? So combustion is similar to how alkene goes through combustion. We'll talk about it quite, we won't be elaborating on this, but generally it's the same logic, right? So basically, there's two different types. There's complete combustion, and there's also incomplete combustion, right? Depending on how much oxygen you have for the reaction to happen, right? So in complete one is when you have excess O2, you will form CO2, and you will form H2O. For incomplete one, you have limited O2, and then you form CO, you will form carbon, etc., etc. There will be H2O as well. Right? So it depends on what is the product that's being mentioned. But addition reaction is the one that's interesting because alkane has this substitution, if you recall. But alkene will have this thing called addition reaction. So what exactly is addition reaction? In an addition reaction, an unsaturated organic compound actually combines with another substance to form a single new compound. Basically, addition, add them together. So what happens here is that the carbon-carbon double bond will actually break to form new single bonds. So if you look at your the page that you have here, right? If you imagine this as alkene, so over here is an ethene with 4H here. What it means is that now the carbon-carbon double bond will actually break. Right? So one of the lines actually break it up, and then you will actually accept the X and Y atom that is over there. This is what we term as addition. Right? So let's take a look at an animation, just a short animation to see what it looks like. This is how the alkene could look like. This is maybe ethene, right? Because it has a formula of C2H4. Right? Look at the middle part whereby you see the carbon-carbon double bond. It's like holding hands together, right? So this is a bond whereby the carbon are sharing electrons. When a reaction happens for addition, let's say another molecule comes along, a suitable molecule comes along. What will happen is that the alkene will actually open up one of the bond. Take note, it's just one of the bond, not both of the bond. Then the new molecules will actually split up and then join back to the alkenes. Then this will form a whole new compound. So if I just run through this again, now as mentioning, the alkene will actually break the one of the line of the double bond. The new molecules will actually add on separately, so they'll split up and then they add one to each of the carbon. And now if you look at it together, right, each of the carbon still have 4 bonds, right? So this is the logic of what we were trying to say earlier, but it's an addition because you have added in the molecule into the alkene. Okay, hope this is a bit clearer. We'll take a look at some examples over the next few slides. So one of the things that you must know for alkene is that there is a total of 3 types of reactions when it comes to addition that you must know. This is the first type, which is addition of hydrogen. What must you know over here? You must know that we are adding what chemical, you must know what is the condition, and you must know what is being formed. So the condition over here is a temperature of specifically 200 degrees Celsius with nickel as a catalyst. Specifically, alkenes are being produced. Right, if you look at the last equation on this screen, you'll realize that they're showing you how an alkene actually breaks up the CC double bond. Then they accept in the new hydrogen. and hence it forms the alkane molecule that you see on the right hand side. Now this is what the addition of hydrogen looks like, right? The concept is going to be the same, just that the chemicals that you add in will be different. The second one that you must know, sorry, not the second one, similarly, just to expand a bit on the first one on hydrogen, right? It's used to convert vegetable oil into margarine. This is actually an application process. You know the vegetable oil that we use for cooking, you know the margarine that we use to spread on bread, etc., right? So vegetable oil can actually be converted into margarine through the process of hydrogenation. So vegetable oils are what we call polyunsaturated molecules. That means they have poly means many, unsaturated means CC double bond. So they are a special kind of alkene-like structure with many of the CC double bond. If you look at the drawing over here, you'll see multiple of the CC double bond. There's one over here, there's one over here, there's one over here, and there might be even more because it's just a part of the structure, right? So what happens is that if you were to add hydrogen, right, when you add hydrogen, you actually convert all the double bond into your single bond, right? So what happens is that now all these double bond will disappear. You just become a single line between the two carbon. Then you have new hydrogen. It'll be a single line between a new carbon, two carbon. Then you have new hydrogen, single line between the two carbon. You have new hydrogen, something like this, right? A bit messy over here, but this is generally the idea of what it means when you do hydrogenation to a whole big molecules, right? Then you actually get to change the vegetable oil into margarine. Okay, the second important one for alkene is this idea of bromination. Now this is very important. I can't emphasize this enough. You do need to know that the reagent that's used here is just aqueous bromine or bromine solution. There's no need for any conditions, but please take note of how to describe the observation. Because bromine is a reddish brown liquid, and what happens when in this reaction is that the reddish brown bromine, not the alkene or alkene, will actually be decolorized or you will turn into colorless. I want to take this point to highlight that you must mention about the starting color as well as the ending outcome. It is a requirement for O level, right? You cannot just mention about the starting color without talking about the ending outcome. In terms of the equation wise, in terms of the drawing, what you'll look like is, imagine you have an alkene here. Let's say I use ethene as an example, reacting with bromine. Because it's an addition reaction, what happens is that the double bond will break, and then you can actually welcome and bring in your bromine individually. And in this reaction, what happens is that because at the start the reddish brown bromine was present, and at the end there's no more reddish brown bromine, so end up with just a colorless liquid that you're looking at. So what you'll see is something that you see on the right hand side on the screen here. Basically, if you have, let's say, an oil that contains the unsaturated hydrocarbons with bromine solution, this bromine solution is actually reddish brown. Once you add it in, right, a reddish brown liquid will actually disappear, and that's where you get your colorless final product. Okay, we'll watch a video to see how this actually looks like. Okay, and you realize that this equation is very important. This reaction is very important because it helps us to differentiate between your alkene and alkanes. Because only for alkene does this reaction happen very quickly. In the case of alkane, there needs to be UV light for any kind of reaction. So there's no way that the reaction will happen if you don't provide any form of UV light. So this is actually one way that we use to differentiate between alkene and alkane. In the next video, you're gonna watch. In the next slide, you're gonna watch a video. It will show you alkene and alkane, and they both look colorless, and they will both actually give off the similar smell, and there's no way that you can tell them apart. But once we add in the reddish brown bromine, and when you see a reddish brown bromine reacting and decolorizing, right, or turning colorless, that's where you can realize that, hey, that means that test tube is actually containing alkene, right? So let's take a look at the video. So now in the video, they're actually adding in the reddish brown bromine, right? So each time when you add in the reddish brown bromine to the alkane, you realize that they just stay there, and over time the reddish brown bromine just continue to remain in the color. The whole test tube just turns into reddish brown, right? It doesn't decolorize. So that's why alkane on the left hand side. Both started off as colorless. For the alkene, you realize that each time when you add in the bromine actually turns from reddish brown to colorless, basically it kind of decolorizes. And this is actually a sign to tell us that the test tube on the right hand side is actually an alkene, because only alkenes can cause bromine solution to decolorize rapidly. Okay, and that's the idea of bromination. So bromination is actually a very important way that we use to test for unsaturated compounds. So in a way, this is basically like how it's like a QA, right? But for organic chemistry, is how we help us to identify the unsaturated hydrocarbons, which are the alkenes. Okay, so that was the second one. The third very important equation that you must know is about addition of steam, which is called hydration. Steam is essentially just H2O in the gaseous form. What must you know over here? You need to know about the reagents. You need to know about the conditions as well as what is being formed. Now, the reagents is steam. The conditions is a bit unique. It's 300 degrees Celsius temperature, 60 atm pressure, and we use this acid called phosphoric 5 acid as a catalyst. And this reaction is important because it then helps us to form alcohols. Now, alcohols is something you're going to learn in the next part of organic chemistry. But first, let's understand how the structural equation looks like. So, assuming that I have an alkene over here, C2H4, ethene, when I react this with an alcohol, which is H2O, the reaction will involve addition. That means my alkene will actually have the double bond, one of the line, being broken to form new bonds. To form new bonds, and the new bonds will comprise of one of the H from the water, H2O, and the other one will be the OH. And together this will be called an alcohol. So in terms of name-wise, this is called ethene, and this is actually what we call ethanol, which is something you're going to learn in the next part of organic chemistry. Right? This is a very important equation because that's how we actually form alcohol from alkenes. So these are the three main addition reactions that you must take note of. From addition of hydrogen to the addition of bromine, in terms of a color change as well, to the addition of steam. Just these three, right? But the concept is the same. The double bond must break and then it accepts in the new atoms. The last slide of this entire video, we are going to learn a bit about this concept called polymerisation. Now, polymerisation sounds like a very complex concept. It is a big concept by itself. But if you think about it for a second, when you look at alkenes, you may be wondering, what if I have two alkenes that are being brought together to each other? Can they add on to each other? That means, is there a way for the alkene to break the double bond but add towards each other? That's why you have polymerization. So in the last slide over here, this is what we call addition polymerization. So polymerization is a process whereby many small molecules called monomers come together to join and form a large molecule called a polymer. Now this requires a certain conditions of high temperature as well as high pressure. And the formula is being shown over here with the equations, etc. Now this is actually a process that we use to make plastics, and plastics are known as polyethylene. Okay, so for now, not to worry too much, this will be covered in greater details in the next set of notes when we do a deeper dive into polymers. And with that, we have come to the end of the series of videos on the chapter of hydrocarbons. So we started off by learning about what homologous series are. We talked a bit about functional groups. We are introduced to the 4 different types of homologous series. Then we move on to talk about alkenes, and then we end off with alkenes. And with each of them, we focus on their drawing, their formula, their naming, their physical properties, as well as their chemical properties. Right, so take note of the different types of things that you learn for each of them. Take some time to consolidate your thoughts, and then you can try the questions that's present within the worksheet itself.